So every virtual address space layout there is has its own page directory and set of page tables. And every unique value for the page directory base register identifies that virtual address space, and thus every process is identified by its virtual address space and by the unique CR3 value. So this is how it works. We have the CR3 register, which points to the physical address of the page directory. And if you take a linear address, the first 10 bits are indexed into the page directory. There you have the address of the page table, which you reference or index into by the next 10 bits, which contain the page table index. And this actually leads to the physical page that we want to access, and the last 12 bits describe the address within that physical page. Now we know, well, we have at least a way to tell processes apart from a scheduling perspective, but we still don't know about the current process. So if we were to use our analysis code on the guest system, we could use all kinds of Windows API calls to determine what's going on. We could have a look at the process list. We could query information about every process, stuff like that. But we're outside of the guest operating system, so we must find another way to do this. And for this, we take advantage of a feature that is used by Windows, and I think by Linux as well, called segmentation. Not as it was originally intended, that is to just, what you see here is two descriptor tables. You have segment selectors that index into these tables and reference segment descriptors. And every segment descriptor, in the most trivial case, specifies a base address, that is a virtual address that denotes the start of the segment, and then you have a limit that determines how far you can go. And then you can do segment-based addressing. That means you specify the segment and an offset, and the offset is basically added to the base, checked against the limit, and if everything's fine, the memory access succeeds. And this can be used for actually separating code and data and stuff like that, but nobody does that anymore, as far as I know. But it is used by Windows, for example, to keep a quick way of accessing certain data structures. So this is in kernel land. The FS segment register normally contains segment descriptor or segment selector 30, which leads to segment descriptor 30, and you can see certain data structures here. This is the kernel processor control region, which contains a link and also the actual data of the processor control block, as far as I know, which in turn references the data structure determining the current thread, and from there you can find data structures describing the process. You can see here the page directory base address is referenced as well. You can see the process ID. You can have the links that is in the connected list of other processes on the system. You have the first 16 bytes of the file name that was used to spawn the process, and you have some more information on the process environment log. This is not all documented very well. You find information such as this normally from the reverse engineering or rootkit communities. And some more information. Within the PED, you can reference, for example, a list of DLLs that are mapped into a process's type of space. And if we determine, for example, by checking the file name that we're interested in the current process, we just switch fine-grained instrumentation on. And fine-grained instrumentation just records all memory writes. monitors all branch instructions, and whenever a branch target lies within modified memory, this means that there was some new code generated on the fly in memory and the process branch there. So this is a symptom of unpacking, of unpacking in memory. So whenever this happens, we take a memory dump. So we just dump the whole memory area to a database. This is also the case for certain branch instructions. So certain branches are also locked, and you can also decide to just basically lock all writes and branches to the database, but this leads to method slowdown. Because you're looking at several 100,000 branches and writes for a single executable, hundreds even millions. What we want to dump is described by another structure in memory, the so-called virtual address descriptor tree. This is used by the kernel to keep track of what's going on within a process's virtual address space, where the heap is, where the stack is, what kinds of memory map files are there. So this is a fairly reliable source of information. So this is how we can make sure we dump the correct memory range. And some unpackers execute in multiple stages, so they unpack first a bit, then branch there, execute some more, unpack some more, and branch again. We want to account for that as well, and sometimes people also just use multiple unpackers, one after the other. That means we have to continue execution and see whether some more comes up. But we don't want to take note of any local branches anymore within that modified memory region. So we mark the memory as clean and then just continue